All right, let's get into it. Today, we are cracking the code of alkenes, a really core topic in organic chemistry. This is an exam-focused explainer from all of us here at Tutorial Haven, and it's designed to give you exactly what you need to walk into that exam feeling confident and prepared.
So, here's our game plan for today. We're going to start by meeting the alkenes. Then we'll dive into the tricky, but super important concept of isomers. After that, we'll master the naming game, figure out what makes them stable, and then we'll wrap it all up with a quick rundown of your exam essentials. Sound good? Let's go.
First things first, let's meet the alkenes. Getting this foundation right is so key because literally everything else we talk about is going to build from here.
So what's the one thing, the single most important feature of any alkene? It's that carbon-carbon double bond. You can find this bond right at the end of a chain. We call that a terminal alkene, or somewhere in the middle, which would be an internal alkene. Heck, it can even be part of a ring, and you guessed it, we call those cycloalkenes.
Okay, here's the textbook definition you want to have locked and loaded for your exam. An alkene is simply a hydrocarbon that's got at least one carbon-carbon double bond. And hey, you might see them called olefins sometimes, so don't let that throw you off. It means the exact same thing. But what is that double bond actually made of? It's not two identical bonds, which is a common mistake. It's actually a mix. You have one super strong sigma bond and one weaker, more exposed pi bond. This combination is what forces all the atoms into a flat shape. And that weaker pi bond, that is the secret ingredient for understanding almost all of an alkene's chemical reactions. Remember that.
Right. This unique bond structure leads us straight into one of the most important concepts for alkenes, isomerism. This is where you have molecules with the exact same formula but totally different structures, and as a result, different properties.
So here's a question for you. A single carbon-carbon bond can spin around freely, kind of like an axle on a wheel. But why can't the double bond do that? What's stopping it? Why is it locked in place?
And the answer comes right back to that pi bond we just talked about. See, in order to rotate that molecule, you would have to physically break that pi bond, and that takes a ton of energy, so it just doesn't happen. And this rigidity, this inability to rotate, is what creates a special type of isomerism called geometrical isomerism.
This whole no rotation thing basically creates two main forms. Since the atoms are locked down, you can have a cis isomer, where the important groups are on the same side of the double bond, or you can have a trans isomer, where they're on opposite sides. Same atoms, but a completely different arrangement in 3D space.
Let's just make this crystal clear, because this is a classic exam question. Cis, same side. Trans, opposite sides. It's a really simple rule, but it's absolutely crucial for being able to identify and name these molecules correctly.
Okay, big exam tip coming up here. Cis and trans work perfectly when you've got two similar groups to compare. But what happens if you have 3 or even 4 different groups attached to that double bond? Well, the cis-trans system just falls apart. And for that, we need a more powerful, more universal system called EZ notation.
The EZ system is all about assigning priorities. Here's how you do it. For each carbon in the double bond, you look at the atoms directly attached and find the one with the highest atomic number. That's your high priority group. Now, if your two high priority groups are on the same side of the bond, we call it Z. That's from the German word zusammen, for together. If they're on opposite sides, it's E for entgegen, which means apart. See, there's a logic to it.
All right, brilliant. Now we can identify all these different structures, so let's learn how to give them their proper names using the IUPAC system. Honestly, mastering this is a guaranteed way to scoop up easy marks in an exam.
It's really just a simple 3-step process. First, you find the longest chain that actually includes the double bond, and you change the ending of its name to -ene. Step 2, and this is the crucial part, you number that chain to give the double bond the lowest possible number. And finally, you just name and number all the side groups, the substituents, just like you would for a regular alkane.
Excellent. So now we can identify them, we can name them. Let's check out how an alkene structure affects its stability and its physical properties, like boiling point.
When we're talking about alkene stability, there's a really clear pattern. And the rule is simple. The more stuff you have attached to the double bond, so the more non-hydrogen groups attached to those carbons, the more stable the whole molecule is. So you want to commit this hierarchy to memory. Tetrasubstituted is the most stable, then tri, then di, and last of all, monosubstituted. And here's a little extra detail.
If you're comparing two dissubstituted alkenes, the trans isomer is usually more stable than the cis one. Why? Well, because its bulky groups are further apart, so there's less crowding.
And this difference in structure has a direct impact on physical properties. Look at the cis isomer. The little electrical poles, the dipoles, they all add up, making the whole molecule a bit polar. That leads to stronger forces between molecules and a higher boiling point. But in the trans isomer, those dipoles cancel each other out, making it nonpolar and giving it a lower boiling point. It all connects.
Okay, you're doing great. We have covered a lot of ground. So let's do a quick fire review of the absolute must-know facts for your exam. Think of this as your final checklist. Takeaway number 1. Always remember the core idea. That carbon-carbon double bond is locked. It's rigid. It cannot rotate. Everything else we've talked about starts from this one fact.
Number 2, this rigidity is the direct cause of geometrical isomers. For your exam, you have to be able to spot cis versus trans, and know when you need to use the more powerful E/Z system instead.
Takeaway number 3 is the simple rule for stability. The more crowded that double bond is with other groups, the more stable the alkene will be. This is a super common question when you have to compare different molecules.
And finally, takeaway number 4. For isomers, remember, cis means same side. This usually creates an overall polarity, which makes it more polar and gives it a higher boiling point than its nonpolar trans twin.
And there you have it. You've just walked through all the fundamental building blocks of alkene structure and properties. With this foundation, you are absolutely ready to go out there and tackle any exam question that comes your way. Seriously, you've got this. Thanks so much for learning with Tutorial Haven.